Okay, so projections and dot product part 2. Okay, so we're going to look at some uh, algebraic vectors for this part and get things sorted out so that we can do dot product and projections with algebraic vectors. Okay. So we know that u dot v is the magnitude of u times the magnitude of v cos theta. And that second part, magnitude of v cos theta, is the scalar projection of v onto u. Okay? If that's true, then we can divide both sides by magnitude of u, and we get the scalar projection of v onto u as u dot v divided by the magnitude of u. So I'm just bringing the magnitude of u over here. So there's a formula for the scalar projection in terms of the dot product, which we didn't have before. Okay. Also, the scalar projection of u onto v would be u dot v over the magnitude of v. So one way to remember it is the one on the bottom is the one you're projecting onto. Okay, some simple formulas to get with the dot product. Since the projection as a vector, so the vector projection equals the scalar projection of u onto v times the unit vector v, well, we can just do some substitutions in here. We know what the scalar projection is. It's u dot v over the magnitude of v times v hat now. So this was the scalar projection that we just found up here. Plug some more in. Well, we know the formula for v hat, or the unit vector v, is v over the magnitude of itself. We can now take that and multiply it by that scalar, and we get this nice little formula here. Okay. Or we realize that we can work backwards here. A vector multiplied by itself, or dot product with itself, is just itself, the magnitude of itself squared, so you can work backwards and you can write it like this. Okay, so u dot v over v dot v times vector v. So that is the vector projection. So we have a bunch of different formulas here for the vector projection that we can use. Okay. So this gives us the projections in terms of the dot product. These formulas become more useful when we look at dot product with coordinate or algebraic vectors. Let's take a look at some of that. All right. So let's let vector u equal u1 and u2. These are the x and y coordinates. Vector v is v1 and v2. These are the x and y coordinates in R2. Okay. Then u also equals u1i plus u2j. I and j are the unit coordinate vectors. Okay, so unit vector in direction of the x-axis, and the unit vector in the direction of the y-axis. Same here. So now we're writing them as vectors, and let's see what happens here when we do the dot product. Okay, so the dot product u dot v, well, we can write these out. u1i plus u2j dot v1i plus v2j. Okay. We're going to use the distributive law. We know we have that now. I haven't proven it to you, but it is in the textbook. Okay. So we're going to distribute the u1i into these two. So we call that FOIL, right? So first, outside, inside, last. So u1i dot v1i plus u1i plus v2j, u2j plus v1i, and u2j plus v2j. I and j are perpendicular. So what do we know about these dot products? Well, when they're perpendicular, they're 0. Okay? So these two end up being 0, which makes this really nice. Okay? So all we're left with then is u1 times v1 times I dot I, u2 times v2 times j dot j, we know that I dot I equals the magnitude of I squared, which is 1. Same with j dot j. So those two are equal to 1 and gives us this nice formula here, which is u1 times v1 plus u2 times v2. So when you're multiplying two coordinate vectors or algebraic vectors, you're really just multiplying the x coordinates and adding it to the product of the y coordinates. Okay, so there's a nice little formula there. So any coordinate vectors xy dot xy is just the x coordinates multiplied plus the y coordinates multiplied. Okay, this is also true in R3. So in 3 dimensions, this is the same sort of thing. Okay, so 3-dimensional vector dot a 3-dimensional vector, multiply the x's, multiply the y's, multiply the z's, add them all together. And you can check that out. You should verify that yourself using the same method that we did in R2. Okay. Here's an example. Let u equal 1, 2, negative 4, v equal 3, negative 1, and 2. Let's look at their dot product. Well, u dot v, we'll write them out in the coordinates, and then we just multiply them. 1 times 3 is 3. 2 times negative 1, negative 2. Negative 4 times negative 4 times 2, negative 8. And you get negative 7 when you add that all together. Okay. What if I asked you to determine the angle between those vectors? Well, let's look at our formula for that. So we've got the dot product is magnitude of u times magnitude of v times cos theta. We rearrange it to get cos theta, and we can sub these in. Well, negative 7 was the dot product, and here's how we find the magnitudes of the vectors. Okay, the square root, so the 3-dimensional Pythagorean theorem. Okay, plug in all those numbers, and you get this nice decimal here, approximately negative 0.4082. And when you do the cos inverse of that, you get 114.1 degrees. Makes sense because the dot product was negative. So the angle between the two should have been greater than 90. And it is. Okay. That's it for that example. Let's look at some projections here. So using the projection formulas with dot product, so the projection of u onto v is u dot v over v dot v times the vector v. This gives us a scalar. This is another way of looking at it. Okay, so that's one of our other formulas that we did earlier. Okay. Plug it all into those formulas. I'm using this one here. The magnitude of v is the square root of all this, but then you square it, gets rid of the square root. Then you multiply it by the vector v. Okay, so you get negative 7 over 14 times vector v, which is going in the opposite direction of vector v, and it has 7/14 of the size, which is negative 1/2. So 1/2 the size of vector v in the opposite direction is the projection of u onto v. Okay, and that's in 3 dimensions. Okay, what about the scalar projection of u onto v? Well, here's the formula that we have for that. And we plug the numbers in. U dot v was negative 7. Magnitude of v was root 14. Plug it in, and that's what we get for that. Okay. Now, so using the dot product to find the angle of a vector with the coordinate axes, x, y, and z. Okay, so this is a bit of an application of it, and it becomes quite useful. So we want to find the angle between any vector and the axes x, y, and z. Okay, so let u, any vector, be a, b, and c. So let a, b, and c be the coordinates of the vector. Okay, could have been x, y, z, could have been whatever you want. Okay, recall that cos theta equals u dot v over the magnitude of u times the magnitude of v. If v equals the vector I, which is the the vector in the x direction, the unit vector, we can find the angle between u and the x-axis. Okay, so we're going to let this angle be called alpha. All right, so cos alpha. This is using this formula here, but instead of vector v, I'm using vector I. So cos alpha equals u dot I over the magnitude of u times the magnitude of I. The magnitude of I is 1. Okay. Vector I is this one. When we do this dot product, it's a times 1 plus b times 0, 0, plus c times 0, which is 0. So the top just ends up being 1. The magnitude of u is this right here, which we know. So this ends up being the cosine of the angle between that vector and the x-axis. Okay. Similarly, if you let beta and gamma be the angles with the y and z-axis respectively, then you get these as the formulas for cos beta and cos gamma. Do it exact same way, but with vectors j and vectors k, you're going to do the dot product. Okay. Now, alpha, beta, and gamma are called the direction angles. So these have a name. They're called the direction angles. And cos alpha, cos beta, and cos gamma are called the direction cosines. So the cosines of the angles are called the direction cosines. Okay. And interesting stuff about that is that the direction cosines form a unit vector in the direction of u. Okay, and this can be shown quite easily. So let's write it out. So the direction cosines, cos alpha, cos beta, cos gamma, write them out as a vector, x, y, and z. Well, these are what they are: a over the magnitude of u, b over the magnitude of u, and c over the magnitude of u. Well, we can factor that constant factor out, which is 1 over the magnitude of u, and then we have the vector u again. Well, we're just going to write that down then. So 1 over the magnitude of u times vector u, well, that's defined as the unit vector u. Okay, so the direction cosines form a unit vector in the direction of u. And an example here. Let 1, 1, 1 be vector u. Well, cos gamma equals this, a, which is 1, over the magnitude of that vector. It also equals cos beta and cos gamma because the coordinates are the same. So we get 1/3 is cos alpha, and if we do cos inverse of 1/3, we get 70.53 degrees. And that's going to be the angle with each of the axes because the coordinates are all the same. So the vector 1, 1, 1 has an angle of 70.53 degrees approximately with the x, the y, and the z-axis. Okay, and 1/3, 1/3, 1/3 is a unit vector, and it's the unit vector in the direction of u. Okay, so that's it for part 2 of dot product and projection.